Okay, in this problem we're told there's a light ray that passes from water to glass and then to air. We're also told to find the largest angle that the incoming ray can make to the normal of the water glass boundary, so that there's still going to be some transmission to the light ray, into the air. And the implication here is that there's some angle of incidence to the water, but we won't get any transmission at the glass-air boundary. And that's true. At the glass-air boundary, we can have a possibility of what's called total internal reflection. That is, if the incident angle is great enough, there won't be any transmitted light. It'll all be reflected. And so the key here really is to figure out what that critical angle is at the glass-air boundary and relate it back to the water angle of incidence. Okay, let me draw this with a little bit bigger figure so we can see things more easily. Here I've got my glass region. There's a water region up top. There's an air region down here. I know that I may have some incident light. I can label the angle of incidence as theta. That's going to transmit, and I can call that transmitted angle alpha. This transmitted ray will then proceed and hit the back surface. By trigonometry, I know that the angle here is alpha as well. So let's calculate the critical angle alpha between the glass-air boundary, where I won't get any transmission anymore. Namely, there's going to be some critical angle alpha c, where I'm going to get total internal reflection. And that's going to be equal to this. Sine alpha c is equal to the index of the air over the index of the glass. Now I can calculate what this is. We'll see that's actually not necessary. This gives us a value of alpha c, where we're going to get total internal reflection. Let's relate that back to theta. Well, we do that using Snell's law. I can see that 1.33, the index of the water, times sine theta, the angle of incidence in the water, is going to be equal to 1.50 times sine alpha. Well, when alpha is equal to alpha c, I can then plug the value in, and I get 1.50 times sine alpha c is just 1 over 1.50. And so in fact, what I find here is that when I get total internal reflection at the glass-air boundary, it's true that 1.33 times sine theta is equal to 1.00. Well, I can solve this for theta and find that the total internal reflection at the glass-air boundary occurs when theta is equal to 48.8 degrees. And that's the answer to the problem.